National Electrical Code Section 240.4b states the ampacity of the overcurrent protective device of a circuit supplying an overhead service entrance conductor or conductors shall not exceed the ampacity of the overhead service entrance conductor or conductors. Section 250.66 states service entrance conductors shall not be smaller than the size given in Table 310.15b16 for service entrance conductors. Table 310.15b16 specifies the minimum ampacity of service entrance conductors for residential occupancies as follows. Firstly, for 100 amperes or less, 3 copper or 4 aluminum or copper-clad aluminum conductors, not smaller than 8 American wire gauge. Secondly, over 100 amperes, 3 copper or 4 aluminum or copper-clad aluminum conductors, not smaller than 6 American wire gauge. Based on the National Electrical Code, there is no minimum circuit breaker size requirement for residential service entrance conductors. However, the overcurrent protective device such as the circuit breaker must not exceed the ampacity of the service entrance conductors. For commercial occupancies, the specific requirements may vary depending on the local electrical code and the type of commercial establishment. It is recommended to consult with a qualified electrician or electrical engineer for guidance on commercial installations. Let's delve deeper into the intricacies of circuit breaker sizing, particularly concerning residential versus commercial applications, while keeping the National Electrical Code as our guiding reference. We will focus on the specific sections and tables mentioned, elaborating on their significance and practical implications. First, it's crucial to understand the role of overcurrent protection. Circuit breakers, as overcurrent protective devices, are designed to safeguard electrical circuits from excessive current, which can lead to overheating, insulation damage, and potentially fires. The National Electrical Code mandates that these devices be carefully selected to protect both the conductors and the connected equipment. Section 240.4b of the National Electrical Code directly addresses the relationship between the ampacity of the overcurrent protective device and the ampacity of the overhead service entrance conductors. Ampacity, in simple terms, is the current carrying capacity of a conductor. This section emphasizes that the circuit breaker protecting the overhead service entrance conductors must not have a higher ampacity rating than the conductors themselves. This is to ensure that the conductors are adequately protected and won't be subjected to currents beyond their safe carrying capacity. To illustrate, if you have overhead service entrance conductors with an ampacity of 100 amps, the circuit breaker protecting them should not exceed 100 amps. Using a larger circuit breaker, say 125 amps, would defeat the purpose of overcurrent protection and could potentially allow the conductors to overheat under fault conditions. Next, Section 250.66 of the National Electrical Code comes into play when determining the appropriate size of service entrance conductors. It directs us to Table 310.15b16 for guidance on selecting conductors of adequate size for service entrance applications. Table 310.15b16 provides specific requirements for residential occupancies, outlining the minimum ampacity of service entrance conductors based on the size of the service. For services rated at 100 amps or less, the table specifies that 3 copper conductors or 4 aluminum or copper-clad aluminum conductors must be no smaller than 8 American wire gauge. For services exceeding 100 amps, the minimum size increases to 6 American wire gauge for the same number of conductors. The significance of these minimum conductor sizes lies in ensuring that the service entrance conductors can safely handle the anticipated load of the dwelling unit. Undersized conductors can lead to voltage drop, inefficient operation, and potentially overheating. Now let's address the initial question regarding a minimum circuit breaker size of 20 amps. Based on the National Electrical Code, there is no specific minimum circuit breaker size mandated for residential service entrance conductors. The primary concern is that the overcurrent protective device should not exceed the ampacity of the conductors it protects, as stipulated in Section 240.4b. While there is no explicit minimum size requirement, practical considerations often dictate the use of circuit breakers rated at least 15 or 20 amps for individual branch circuits within a dwelling unit. These circuits typically supply lighting, receptacles, and small appliances. The choice of circuit breaker size depends on the anticipated load of the circuit and the ampacity of the conductors serving it. For commercial occupancies, the electrical requirements can be more complex and may vary depending on the type of establishment, the connected loads, and the local electrical codes. Commercial buildings often have larger electrical services, more diverse loads, and stricter safety regulations. Therefore, it's essential to consult with a qualified electrician or electrical engineer for guidance on commercial installations. These professionals can assess the specific needs of the building, perform load calculations, and ensure compliance with all applicable codes and standards. In summary, when sizing circuit breakers and conductors, it's crucial to consider the following factors. Firstly, conductor ampacity. The ampacity of the conductors must be sufficient to carry the anticipated load. Secondly, overcurrent protection. The circuit breaker or fuse must protect the conductors from overcurrent conditions. Thirdly, voltage drop. The conductors must be sized to minimize voltage drop and ensure efficient operation. Fourthly, applicable codes and standards. All installations must comply with the National Electrical Code and any local electrical codes. While the National Electrical Code provides a comprehensive framework for electrical installations, it's important to remember that it's not a substitute for sound engineering judgment and professional expertise. Consulting with qualified professionals is always recommended, especially for complex or critical applications. Here are some additional points to consider regarding circuit breaker sizing and conductor selection. Ambient temperature. The ampacity of conductors is affected by ambient temperature. High temperatures reduce the ampacity of conductors, so appropriate adjustments must be made. Conductor insulation. The type of insulation used on conductors also affects their ampacity. Different insulation types have different temperature ratings, which must be considered when selecting conductors. Grouping of conductors. When multiple conductors are bundled together, their ampacity must be directed to account for the increased heat generated. Continuous loads. For circuits supplying continuous loads, the overcurrent protective device must be rated at not less than 125% of the continuous load. This is to prevent nuisance tripping of the circuit breaker. Non-linear loads. Circuits supplying non-linear loads, such as electronic equipment, may require special considerations to prevent overheating of the neutral conductor. Harmonics generated by these loads can cause excessive current flow in the neutral conductor. In conclusion, understanding the principles of circuit breaker sizing and conductor selection is essential for ensuring the safety and reliability of electrical systems. By adhering to the National Electrical Code and consulting with qualified professionals, you can create electrical installations that are both safe and efficient. Always prioritize safety and seek expert advice when dealing with electrical systems. Electricity can be dangerous, and it's crucial to take all necessary precautions to protect yourself and others. Remember to turn off the power before working on any electrical circuits and to use appropriate personal protective equipment. If you're not comfortable working with electricity, it's best to leave it to the professionals. They have the knowledge, skills, and tools to perform electrical work safely and effectively. Furthermore, it's important to stay informed about changes to the National Electrical Code and other relevant standards. The electrical industry is constantly evolving, and new technologies and practices are emerging all the time. By staying up to date, you can ensure that your electrical installations are safe, efficient, and compliant with the latest requirements. Finally, remember that electrical safety is everyone's responsibility. By promoting safe electrical practices and educating others about the hazards of electricity, we can help prevent accidents and injuries. Let's all work together to create a safer electrical environment for ourselves and for future generations. Now let's talk more about specific examples. Consider a residential dwelling unit with a 100 amp service. According to Table 310.15b16 of the National Electrical Code, the minimum size conductors for this service would be 8 American wire gauge copper conductors. The overcurrent protective device protecting these conductors should not exceed 100 amps. Within the dwelling unit, individual branch circuits would typically be protected by 15 amp or 20 amp circuit breakers. These circuits would supply lighting, receptacles, and small appliances. For larger appliances, such as refrigerators, washing machines, and electric dryers, dedicated circuits with higher ampacity ratings would be required. For example, an electric dryer might require a 30 amp circuit, while an electric range might require a 50 amp circuit. In a commercial building, the electrical system would be significantly more complex. The service size would depend on the size of the building and the anticipated load. Large commercial buildings might have services rated at several thousand amps. The distribution system within the building would consist of a network of feeders and branch circuits. Feeders would carry power from the service entrance to various distribution panels throughout the building. Branch circuits would then supply power to individual loads, such as lighting, receptacles, and equipment. The circuit breaker sizes and conductor sizes would be carefully calculated based on the anticipated load of each circuit. Commercial buildings often have a variety of specialized equipment, such as HVAC systems, elevators, and industrial machinery. These loads would require dedicated circuits with appropriate ampacity ratings. For example, a large HVAC unit might require a 100 amp or 200 amp circuit, while an elevator might require a 400 amp or 600 amp circuit. In addition to the National Electrical Code, commercial buildings must also comply with other relevant standards, such as those related to fire safety, accessibility, and energy efficiency. These standards can impact the design and installation of the electrical system. For example, fire alarm systems require dedicated circuits and backup power supplies to ensure reliable operation in the event of a fire. Accessibility requirements may dictate the placement of receptacles and other electrical devices. Energy efficiency standards may require the use of energy-efficient lighting and equipment. As you can see, electrical systems can be quite complex, especially in commercial buildings. It's essential to have a thorough understanding of the National Electrical Code and other relevant standards to ensure that the electrical system is safe, reliable, and compliant. Always consult with qualified professionals when designing and installing electrical systems. They have the knowledge, skills, and experience to do the job right. And remember, electrical safety is paramount. Always take all necessary precautions to protect yourself and others from the hazards of electricity. By working together, we can create a safer electrical environment for everyone. Let's consider some specific examples of circuit breaker sizing and different applications. In a typical residential kitchen, you might find the following circuits. 102 20 amp small appliance branch circuits. These circuits supply power to receptacles located on the countertop and are used for small appliances such as toasters, coffee makers, and blenders. A 20 amp refrigerator circuit. This circuit supplies power to the refrigerator and should not be used for any other appliances. A 15 amp or 20 amp lighting circuit. This circuit supplies power to the overhead lighting fixtures in the kitchen. A 30 amp electric range circuit. This circuit supplies power to the electric range or cooktop. In a residential bathroom, you might find the following circuits. A 20 amp small appliance branch circuit. This circuit supplies power to receptacles located near the sink and is used for hair dryers, curling irons, and other personal care appliances. A 15 amp lighting circuit. This circuit supplies power to the overhead lighting fixtures and the vanity light. 20 amp individual branch circuit for an appliance. This circuit supplies power to permanently connected appliances, such as heaters. In a commercial office building, you might find the following circuits. 20 amp general purpose receptacle circuits. These circuits supply power to receptacles located throughout the office space and are used for computers, printers, and other office equipment. A 20 amp lighting circuit. This circuit supplies power to the overhead lighting fixtures in the office. Dedicated circuits for HVAC equipment. These circuits supply power to the heating, ventilation, and air conditioning equipment. Dedicated circuits for elevators. These circuits supply power to the elevators in the building. Dedicated circuits for data processing equipment. These circuits supply power to the computer servers and other data processing equipment. The specific circuit breaker sizes and conductor sizes will vary depending on the size and type of equipment being served. It's important to perform load calculations to determine the appropriate size for each circuit. And remember to consult with qualified professionals to ensure that the electrical system is safe, reliable, and compliant. Let's delve into the nuances of conductor selection, specifically focusing on conductor types and their applications. Conductors are the pathways through which electrical current flows, and their selection is governed by factors such as ampacity, insulation type, and environmental conditions. Copper conductors are widely used due to their excellent conductivity and ductility. They are available in various sizes, ranging from large cables used for service entrances to small wires used for branch circuits. Aluminum conductors are lighter and less expensive than copper conductors, but they have lower conductivity. They are often used for larger feeders and service entrances where weight is a concern. Copper-clad aluminum conductors combine the benefits of both copper and aluminum. They have an aluminum core with a copper cladding, providing a good balance of conductivity and weight. The insulation surrounding a conductor serves to prevent electrical contact with other conductors or grounded surfaces. Various insulation types are available, each with its own temperature rating and suitability for different environments. Thermoplastic high-heat-resistant nylon-coated THHN insulation is a commonly used insulation type for general-purpose wiring. It has a temperature rating of 90 degrees Celsius in dry locations and is resistant to moisture and abrasion. Cross-linked polyethylene XHHW insulation is another popular insulation type known for its excellent moisture resistance and high temperature rating. It is suitable for both wet and dry locations. Mineral insulated MI cable consists of copper conductors insulated with a mineral compound and enclosed in a copper sheath. It is highly resistant to heat, fire, and moisture, making it suitable for harsh environments. When selecting conductors, it's essential to consider the ambient temperature in which the conductors will be installed. Higher temperatures reduce the ampacity of conductors, so appropriate adjustments must be made. The National Electrical Code provides tables that specify the ampacity of conductors at different temperatures. It's also important to consider the grouping of conductors. When multiple conductors are bundled together, their ampacity must be dated to account for the increased heat generated. The National Electrical Code provides guidelines for dating conductors based on the number of conductors in a bundle. In addition to ampacity and insulation type, other factors to consider when selecting conductors include voltage drop, mechanical strength, and resistance to corrosion. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. Conductors must be sized appropriately to minimize voltage drop. Mechanical strength is important for conductors that are subject to physical stress or vibration. Conductors must be able to withstand the forces acting upon them without breaking or becoming damaged. Resistance to corrosion is important for conductors that are exposed to corrosive environments such as those found in chemical plants or coastal areas. Conductors must be made of materials that are resistant to corrosion or be protected by a corrosion-resistant coating. By carefully considering all of these factors, you can select the appropriate conductors for your electrical installation and ensure its safety and reliability. Remember to consult with qualified professionals for guidance on conductor selection and installation. They have the knowledge, skills, and experience to do the job right. And always prioritize safety when working with electricity. The proper selection and installation of conductors is critical to the safe and efficient operation of electrical systems. Let's shift our focus to the practical aspects of overcurrent protection, delving into the types of overcurrent devices and their applications. Overcurrent protection is a vital safety measure designed to safeguard electrical circuits from excessive current flow, which can arise from short circuits, overloads, or ground faults. Overcurrent devices, such as circuit breakers and fuses, are strategically placed in electrical circuits to interrupt the flow of current when it exceeds a predetermined level. Circuit breakers are electromechanical devices that automatically trip and interrupt the circuit when an overcurrent condition occurs. They can be reset manually after the fault has been cleared, making them reusable. Fuses, on the other hand, are single-use devices that melt and interrupt the circuit when an overcurrent condition occurs. They must be replaced after they have blown. Circuit breakers are generally preferred over fuses in most applications due to their reusability and ease of resetting. However, fuses offer some advantages in certain situations, such as their ability to provide faster protection against high fault currents. There are several types of circuit breakers, each designed for specific applications. Molded case circuit breakers are the most common type of circuit breaker and are used in a wide range of applications from residential to commercial and industrial. They are available in various sizes and interrupting ratings. Insulated case circuit breakers are larger and more robust than molded case circuit breakers and are used in high current applications. They have higher interrupting ratings and are designed to withstand harsh environments. Air circuit breakers are used in very high current applications, such as in power distribution systems. They use compressed air to extinguish the arc that occurs when the circuit is interrupted. Fuses also come in various types, each with its own characteristics and applications. Cartridge fuses are the most common type of fuse and are used in a wide range of applications. They consist of a fusible link enclosed in a cylindrical cartridge. Plug fuses are used in residential applications and screw into a fuse holder. They are available in various ampacity ratings. Time delay fuses are designed to withstand temporary overloads such as those that occur when starting a motor. They have a built-in time delay that allows them to ride through short duration overloads without blowing. When selecting an overcurrent device, it's important to consider the following factors. The ampacity of the circuit. The overcurrent device must be rated to protect the conductors in the circuit. The interrupting rating of the overcurrent device. The overcurrent device must be able to safely interrupt the maximum fault current that could occur in the circuit. The type of load being served. Different types of loads, such as motors and transformers, require different types of overcurrent protection. The environmental conditions. The overcurrent device must be able to withstand the environmental conditions in which it will be installed. The National Electrical Code provides detailed requirements for overcurrent protection. It's essential to consult the National Electrical Code to ensure that your overcurrent protection system is safe and compliant. Remember to consult with qualified professionals for guidance on overcurrent protection. They have the knowledge, skills, and experience to do the job right. And always prioritize safety when working with electricity. The proper selection and installation of overcurrent protection devices is critical to the safe and reliable operation of electrical systems. Let's discuss common misconceptions about the National Electrical Code and electrical safety. There are many misconceptions about the National Electrical Code and electrical safety that can lead to dangerous situations. One common misconception is that the National Electrical Code is a law. The National Electrical Code is not a law, but rather a set of standards developed by the National Fire Protection Association. However, many local jurisdictions adopt the National Electrical Code as law, making it legally binding. Another misconception is that the National Electrical Code covers all aspects of electrical installations. The National Electrical Code covers most aspects of electrical installations, but it does not cover everything. For example, the National Electrical Code does not cover the design of electrical equipment. Another misconception is that electrical work is easy and anyone can do it. Electrical work can be dangerous and should only be performed by qualified professionals. It's important to have the knowledge, skills, and experience to do the job right. Another misconception is that it's okay to overload electrical circuits. Overloading electrical circuits can cause overheating and fires. It's important to use the correct size circuit breakers and conductors for the load being served. Another misconception is that it's okay to use extension cords as permanent wiring. Extension cords are not designed for permanent use and can be a fire hazard. It's important to install permanent wiring for all electrical devices. Another misconception is that it's okay to ignore electrical safety rules. Electrical safety rules are in place to protect people from electrical shock and fire. It's important to follow all electrical safety rules. Another misconception is that ground fault circuit interrupters are not necessary. Ground fault circuit interrupters protect people from electrical shock by detecting ground faults and interrupting the circuit. They are required in many areas, such as bathrooms and kitchens. Another misconception is that surge protectors are not necessary. Surge protectors protect electrical equipment from voltage surges. Voltage surges can damage or destroy electronic equipment. It's important to use surge protectors to protect valuable equipment. Another misconception is that it's okay to work on electrical equipment while it's energized. Working on energized electrical equipment can be extremely dangerous and can result in electrical shock or death. It's important to de-energize electrical equipment before working on it. By understanding these common misconceptions, you can avoid dangerous situations and ensure that your electrical system is safe and compliant. Always consult with qualified professionals for guidance on electrical safety. They have the knowledge, skills, and experience to do the job right. And always prioritize safety when working with electricity. Electrical safety is everyone's responsibility. By promoting safe electrical practices and educating others about the hazards of electricity, we can help prevent accidents and injuries. Let's all work together to create a safer electrical environment for ourselves and for future generations.